In this example, we'll find the power series and radii of convergence for the following two functions. So what I'll do here is I'm going to write out the power series from the previous page. We had 1 over 1 minus x. We could write that as a power series as follows. The sum from n equals 0 to infinity of x to the power n, and the interval of convergence was negative 1 x less than 1. So let's take a look at this expression here. So what we have here is instead of 1 over 1 minus x, we actually have 1 over 1 minus 2x. So what we're going to do is we're going to take the same power series and write this is the sum from n equals 0 to infinity. But what we're going to do is we're going to replace x by 2x. So I'm going to put 2x here, and we can clean that up a little bit and write this as the sum from n equals 0 to infinity of 2 to the power n times x to the power n. So that would be our final answer. Now, we also need to find the radius of convergence. So what we do is we write negative 1 is less than, and instead of x, we're going to write 2x, and then less than 1. And so when you solve that for x, you divide all sides by 2, and so you actually see that your interval of convergence for this one is negative 1/2 less than x less than 1/2. So that's our interval of convergence. And we can do something very similar for this expression right here. So when we look at 1 over 1 plus x squared, when we compare that with 1 over 1 minus x, we actually have to rewrite this addition as a subtraction. So I'm going to do that as follows. So I'm going to have 1 over 1 minus, and then to make that work, I'm going to have to subtract negative x squared. And so my power series then looks as follows. N equals 0 to infinity, and then instead of x to the power n, I now write negative x squared to the power n. And then again, I can rewrite that as follows. Sum from n equals 0 to infinity. And then this is negative 1 times x squared. So I can write that as negative 1 to the power n. And then x squared to the power n. That's x to the power 2n. So that is my power series for that function. And then the radius of convergence, well, we start off with negative 1 less than x less than 1. And now instead of x, we write negative x squared. And what you can see is when is negative x squared between negative 1 and 1, you can show that this is, from this, it follows that x has to be between negative 1 and 1. Any value that's bigger than 1, if you square it and take the negative, would be less than negative 1. And the same for any value less than negative 1. You square it, you take the negative, it would also be less than negative 1. So as you can see, that is an easy, relatively easy way of getting these power series for other functions. So we have another trick up our sleeve to find power series, and that is when we look at differentiation and integration of power series. So if the series f of x equals the sum from n equals 0 to infinity of a sub n times x minus x naught to the power n has a positive radius of convergence rho, then f is differentiable in the interval from x naught minus rho to x naught plus rho, or said differently, where the absolute value of x minus x naught is less than rho. And term-wise differentiation gives the power series for the derivative. So f prime of x equals the sum from n equals 1. So please take note of that shift, right? We don't start at 0 anymore, where in the original power series. And then you can see we can just take the term-wise derivative, the n moves to the front, so we get n times a sub n times x minus x naught to the power n minus 1. And this holds for all x minus x naught in absolute value less than rho. So again, that is the power rule applied to each term, and there's a shift in the summation, and that has to do with that the first term of this power series is a constant term, and so when you take the derivative of a constant, that's 0. So for the derivative, the power series starts at 1. Furthermore, term-wise integration gives the power series for the integral of f. So the integral of f of x dx is the sum from n equals 0 to infinity of a sub n over n plus 1 times x minus x naught to the power n plus 1 plus a constant of integration for all x for which x minus x naught in absolute values less than rho, the radius of convergence. And again, you see each term we use the power rule for integration. We add 1 to the exponent, and then we divide by that new exponent. So let's see some examples where we can apply this. So 1 over 1 minus x squared is the derivative of 1 over 1 minus x. So what we can do here is we can say this is the derivative of, and the power series for 1 over 1 minus x is given by summation from n equals 0 to infinity of x to the power n. And what we do there is we take the summation and we take the derivative of each of these terms. So that's n times x to the power n minus 1. And then the important thing to note is that we don't start at n equals 0, but we start at n equals 1. So that is our power series for 1 over 1 minus x squared. And if you write this out, you'll see that the terms for this, the first few terms, for n equals 1, we get x to the power 0, which is 1 times 1. And then for n equals 2, you get 2 times x to the power 1. And then 3x squared plus 4x cubed plus etc. Now, let's find the power series for the arctangent. So the arctangent is the antiderivative of 1 over 1 plus x squared. So we take the antiderivative, and now we need to figure out what the power series of 1 over 1 plus x squared is, but we did that over here. So the power series was given by this expression here. So let's write that out. So it's the sum of n equals 0 to infinity of negative 1 to the power n times x to the power 2n, and then dx. And what we can do is basically pull that integral inside. So this is the summation from n equals 0 to infinity of negative 1 to the power n, and then times the integral of x to the power 2n dx. So let's take a look at that integral. For that integral, we can use just our regular power rule. And so we still have our summation from n equals 0 to infinity of negative 1 to the power n. And then the antiderivative of that, we have to add 1 to the exponent. So that's 2n plus 1. And then we divide by 2n plus 1. Now, at this point, we have to introduce a constant of integration. And so we'll have to figure out what that constant of integration will be. But we have our power series here, and we just have to figure out what is that c. So what we can do, the easiest way to check that is by taking our arctan and plugging in the value 0. So we know that the arctan of 0 is 0. So this equals 0. But when we plug in 0 for this formula, let's take a look at what happens. we plug in 0 here. So this term will be 0 because when n equals 0, we have 0 to the power 1. When n equals 1, we have 0 to the power 3. So we have all the odd powers of x. So this whole infinite sum will be 0 when x equals 0. So let's rewrite this in a different way. Arctan of 0 equals the summation from n equals 0 to infinity of -1 to the power, or to the power n, times 0 to the power n plus 1 over 2n plus 1. And so, as I said before, that whole summation is just 0. And then we add c. And so arctan of 0 is c, but that should be 0. So we see that our conclusion is that c equals 0. And our arctan of x, our conclusion is that arctan of x has the following power series, n equals 0 to infinity of -1 to the power n times x to the power 2n plus 1 over 2n plus 1. And if you want to write out the first few terms, you get x minus x cubed over 3 plus x to the power 5 over 5 minus etc.